Hey guys, welcome to the Astronomy Unit. We're going to be talking about different units for measurement, the planets, the different bodies that are in space. Our first unit of measurement are AUs, or Astronomical Units. The average distance from the Sun to Earth is 1 AU. This is great for measuring between planets in our solar system. For example, Neptune is 30 AUs away. Light years are great for measuring outside of our solar system. For example, if we had a UFO that it took a year for them to see the light penetrating from the sun, they'd be 1 light year away. To put this in perspective, we see the light on the sun about 8 minutes after it actually occurs. Another perspective, the nearest star would take us 4 years to figure out that it may be turned off or something happened on it. Think of this kind of similar to a cell phone. If we send a text message, okay, it probably goes pretty quick to the other phone. If we were further distance away, say a year away, it would take us a year to get that text message away. Lastly, scientists use parsecs when talking about space, and these are larger than light years, roughly 3 times larger. And it takes the idea that if you were to see a star, we could kind of figure out the distance using triangulation. Because of the Earth's movement, we'd see it again, but at a different angle. And using angles, we could figure out the distance in parsecs. On to stars. Now, we learned in kindergarten probably there's a bunch of different types of stars, different shapes. Well, the colors part is true, and they are a little bit different in shape. However, they're mainly just a cloud of hydrogen and helium and a couple other trace gases. Now, when these gases are pressed in because of gravity, they actually kind of explode and they create light. That's why they're so bright. It's because we're having these gases fuse together and create new higher elements. Now, when they do that, they actually have different temperatures, blue being the coldest and red being the hottest, and you see the different ranges in between. Now, let's look at the life cycle of a star. Basically, how does it begin and how does it end? Now, all stars start off as what we call a nebula, and that's basically when particles of gas and dust start kind of compiling and compacting in space. Now, a nebula can break off into 2 parts. It can either be small, or a low mass, or it can be large, a high mass. And these are 2 different star cycles. A low mass star is next a red giant, which means the explosions on that star are getting greater and it's actually expanding. Now, after expanding long enough, there's enough fusion going on, it might turn into a white dwarf, which is actually smaller and more compact, but we lost that atmosphere. And this is kind of where it might fizzle out and die, and maybe become a nebula once again. So the star cycle for a low mass is a nebula, to a low mass star, to a red giant, to a white dwarf. Now, don't forget about that high mass star. So say a nebula became a high mass star, its next step would be to become a supergiant. So now it's even bigger than it was as a low mass. The atmosphere is getting grander to the point where it actually can't control it anymore and it actually explodes. Right? The atmosphere is being sent out, blown out. And once the kind of everything, the dust settles, I guess you'd say, it either become a neutron star, which is kind of like a white dwarf, or a black hole. So you see the process here: a nebula, high mass, to a supergiant, to a supernova, to either a neutron star or a black hole. Now on to the 8 planets in our solar system, all of which meet 3 criteria. First, they orbit around a star, in our case our sun. Second, they're round because of gravity. They're so big that they actually pull in and create that round shape. And third, they have a clear neighborhood, which discounts Pluto, which is no longer a planet, because it doesn't have a clear area to travel in orbit. Our 8 planets are broken up into inner planets and outer planets. The first 4 are inner, or terrestrial, and made of rock. The last 4 are gas planets, and they are made mostly out of gas. We'll take a look at all 8 of these planets individually. First off, we have Mercury, which is the smallest planet, the first and closest to the sun. Has a large iron core, and it actually looks very much like our moon. Next, we have Venus, which is about the same size as Earth, has sulfuric acid rain, a clockwise rotation, and over 160 volcanoes and craters. The third planet is Earth, which is known to have tectonic plates, life, liquid water, the only one with that, one moon, has a revolution of 365.3 days, and a rotation of about 24 hours. Our fourth planet is Mars, known as the rocky red planet, known a lot from movies. We show a lot with active volcanoes, lava flows, we have deep canyons, and even has an ice cap of frozen water. The fifth planet is the largest, as Jupiter. It has 253% more gravity than Earth. It has a really fast rotation of about 10 hours, which creates a lot of winds, henceforth the red spot, which is a storm there. And it's known to have 79 moons. Saturn is the next largest planet, with 150 moons, only of which 62 orbit. One moon even has a unique trait of having geysers on it, and it's known to have huge rings made of icy bodies. Uranus, which is actually tilted on its side, has 27 moons, takes 84 years to revolve around the sun, and has a blue-green color. And our last planet is Neptune, which has a darker blue due to a little bit more methane. It's the smallest gas planet. It's dark blue in color, like we mentioned. Has really strong winds as well. One of the strong storms was the Great Dark Spot, which has actually left, but it's lasted for a long time. We also have other bodies in our solar system: comets, asteroids, and meteoroids. We'll take a look at each of these more specifically. Now, a comet is mostly made out of ice and some dust and maybe a little bit of rock. Okay, it typically does orbit our sun, and actually, because of that, it causes two tails to form. One being a dust tail, which kind of acts like the dirt behind a pickup truck going down a dirt road. It's the direction opposite of where it's heading. And it also has an ion tail, which is actually always directly opposite of the sun. And it's actually the stripping or the evaporation from the sun's heat going the opposite direction. Now, comets originate in either the Kuiper Belt or the Oort cloud. These are two regions that are actually beyond our planets. Kuiper Belt is kind of where Pluto is and Neptune. It's about 25 AU wide. And the Oort cloud is massive with millions and trillions of different objects and rocks. And that's the furthest edge of the Milky Way galaxy. Next up, we have asteroids, which are huge, huge pieces of metal and rock just kind of piled together. They can sometimes be in orbit with the sun, sometimes they are not. But they're mainly located in what's called the asteroid belt. And that's located between the inner planets and the outer planets, if you remember that from earlier. Lastly, we have meteoroids, which are found in space. They're just smaller clusters of rock or metals, sometimes from asteroids, sometimes from comets. And they're actually called meteoroids when they're in space. As soon as it touches the Earth's atmosphere, it's called a meteor. We know those as shooting stars. And if they do make impact on Earth, we call those meteorites. Good way to think about that. Think about little mites on the ground. Okay, they're meteorites. We want to end this unit talking about why do we study space. It's to see the relationships of different objects in space, including our very own Earth and the moon and how that works. We know our Earth rotates on an axis which is slightly tilted, about 23%, and we know that creates different seasons as it spins and orbits around the sun. We also know the moon impacts Earth by pulling with its gravity. For example, how it pulls on the water and creates tides. When the moon's near us, it creates a high tide, and when it leaves, it creates a low tide, or the water level at the beaches go down. And if we actually do look up, we could see effects of all these relationships. For example, if we look at the moon, right? We know what a full moon is. It's where we see a giant reflection back from the sun. There's also different phases it might go through. The first phase we consider as the new moon. We don't see anything. A new crescent, we see a little sliver on the right side. First quarter, we see half of the moon on the right side. A waxing gibbous is most of the moon is visible except for a little piece of the left. The full moon, a waxing gibbous. The last quarter, and we end with the old crescent. Now you might see some names differ. Some people have different names for the different phases, but these are the general ones used. Well, that does it for our astronomy unit. Thanks for watching, and until next time.